there. And this class is on my last teaching day of the week. I've got classes Monday, Tuesday, Wednesday, Thursday. So it makes sense when you think about it that if I'm going to have a day that I have absolutely no energy and I can't show up, it's going to be the last day of the week that there. So that's why this Thursday class seems to get hit more than the others. A couple of times, actually, I think 2 weeks ago, I deliberately skipped like the Wednesday class in order to rest to make sure I had energy for Thursday, but that doesn't always work because I've had Mondays where I've slept all day, literally slept all day on Sunday and could barely get up for work on Monday. This week was actually that way. I mean, if you look at me Monday, I'm really dragging, and even Tuesday, but today I'm okay. All right. I apologize to everyone for if I seem a little unprepared. To be honest, I normally follow my my lectures with motors with a series of lectures on sensors. This time I went and had you do the lab first, and I forgot to come back and finish sensors right there. So then I kind of went off on a tangent talking about the Arduino on Monday, and when I should have really got into the sensors at the. So, and I don't know, hopefully I don't have to do this every time. Okay, I guess so. All right, sensors, the goal of a sensor is actually to measure something in the physical world in a way that a robot or computer or automated piece of equipment can know what's going on in the world around it. Now, when we talk about human sensors, we have 5 that we normally refer to as our 5 senses. Touch, which is the most common one that people think about. You can feel things, feel what they look like. Except for me, my touch doesn't work on these fingers, but regardless, touch is a common one. Our eyesight is considered one of our most valuable senses right there. When you look at eyesight, the blind cannot drive very well. They're coming up with automated cars that can drive themselves. So one of the discussions of that is going to be is that the blind will be able to go out to their car and tell their car where they want to go, but we're not there yet. So you got touch, you've got sight, you've got hearing. We can hear the world around us. We can smell the world around us. Ask anybody from the United States or Canada that goes anywhere near a durian stand whether or not their sense of smell works. Right there. My sister was visiting a couple of months ago. We were having lunch at a Chinese Muslim restaurant there at Edaman. And 2 girls come in and they're secretly carrying this little bag and they're debating whether or not they can open it. And then a few minutes later, the manager of the restaurant kicks the 2 girls out and sets them by the street on a table, and then they cut open their durian and start eating their durian there by the parking lot. But my sister, who is not used to the durian smell, immediately picked it up when the girls walked in the restaurant, even though the durian had not been opened yet. Because my sensor for durian smell is broken. Yeah, I can smell durian when I smell it, but my wife eats that stuff like it's candy. She likes to make some kind of what do they call it? Is it bobo or something where you boil it with put in with sweet potatoes or something? There's a dish, I don't know what it is. I don't eat it. But she likes to eat that, and as a result, our house quite often has a durian smell to it. When I come home, in the evening sometimes, I don't go out in the evenings, but I go outside and I think it's payback because I go outside and I smoke a cigar, and she can't stand the smell of a cigar. So, oh, sorry. I'm talking about durian. I'm already sneezing right there. She can't stand the smell of the cigar, so she'll eat the durian food. But she's got the same sense. But smell is another sense. And then, see, I did touch, smell, hearing, smell, and one more. I just completely drew a blank. What's that? Oh, taste. Our sense of taste. That there. So now, some of these sensors, we have sensors for almost all these, except for even taste. There's sweetness sensors, salty sensors, in the food manufacturing business that they're, because if you're making a batch of chocolate, for example, you need to sense how sweet that chocolate is, in the manufacturing process. Unless you pay somebody like myself who likes to eat to sit there and take a bite out of each batch of cake that comes on the assembly line and say whether it's sweet enough. But there are sensors for the manufacturing process of foods that do taste. So pretty much every one of the five sensors, or five senses, has an equivalent in the electronics world, robots. There are sensors that can smell, right there. One of the sensor products that I worked on once, that there was what they call a alcohol interlock system. And what an alcohol interlock system is that in the U.S., Canada, and Europe, most Western countries, I haven't heard of it in Malaysia yet, but if you get pulled over by the police and arrested for driving while intoxicated, DWI, or driving under the influence, DUI, they call it. Different states use different titles. Some states use both titles out there. So, but regardless, that there, when we look at they put in an interlock system, which basically means that you cannot drive your car until you blow into an alcohol sensor. And what we're looking for was various chemicals in the breath when they blow into the sensor to sense whether the person had been drinking alcohol or not. And what we discovered is that some spicy foods and garlics will fool the sensor. So if you go out for a pizza with lots of garlic and tomato sauce and hot chili peppers on there, and you go to drive your car, the car will register a positive response for alcohol, even though you had not had any alcohol in it. So again, but we were looking for chemicals in the breath that were in a similar way that the nose would look for it, right there. So, obviously we have sensors that will emulate sight. I've worked on many projects over the years where we've used cameras and we've used various light sensors in order to do things. So when we look at our five senses, there's electronic sensors that will emulate all of the five senses and then some. There's things that we can sense electronically that cannot be sensed, that the human body doesn't necessarily sense, right there. One, of course, which is position, GPS, actually uses sensors. GPS doesn't really use a sensor. GPS actually gets radio communications from various satellites with directions between 3 or 4 satellites in order to tell. It's not really a sensor, but the magnetic compass is a sensor, right there. So, again, I'm using these slides for the first time, so I don't necessarily know what slide's coming up. I just quickly scanned them and saw that they covered everything I wanted to cover, and I can make up the rest. Okay. A sensor, by definition, provides a usable output in response to a specified measure. In other words, basically, we have something we want to measure called the measurand, and what the sensor does is it simply gives us an electrical signal that represents what we're measuring. So if we're measuring light, and a bright room might be 255, assuming an 8-bit sensor, a dark room might be 0, a medium split room like this room right here might be 180, 190, that there. The sensor acquires the physical quantity and converts it into a signal suitable for processing. Most sensors that we would deal with in robotics, the output of the sensor is going to be electrical. There are some sensors that will give you a mechanical signal out or an optical signal out, but most sensors are going to be electrical that we work with. So nowadays, common sensors convert. All right, I didn't read that there. You'll hear this term transducer a lot. And what a transducer is it's a device within the sensor that actually changes temperature to a voltage. It changes sound level to a voltage. Usually a sound sensor actually measures differences in pressure, because the way our ears work, without going into a biology lesson which I'm going to anyway, right there. The way our ears work is, here's our ear drum, and it goes down this long tube that gets narrower and narrower and narrower at the end, and this is filled with hairs right there. And the shortest hairs are toward the end of the tube, the longest hairs are toward the beginning of the tube. And when a sound enters the ear, it vibrates the eardrum, which just is filled with a fluid right there. Not a little thicker than water. It's probably more like, I don't know what, it's thinner than honey, but thicker than water, somewhere in between right there. But it's filled with a fluid. And as this vibrates, certain hairs correspond to certain frequencies. So if you have a very deep sounding bass drum, for example, the hairs that are longer are going to be excited. If you have one of the high-pitched keys on a piano, one of the short-pitched noises short hairs is going to be excited. And the amount of excitement will depend on how loud that particular signal is. Now, the human voice is a very complex signal. It looks like this, the human voice. Mine probably looks worse than that, but it's got many, many frequencies to it. A pure tone that comes out of a function generator sounds pretty bland. When you look at a piano key a note might look like this, right there if I hit a particular note there. This here notes primary frequency, and we've got all the various harmonics that contains other things in the note there. Now, when we look at something like the human ear and how it works, it actually uses a logarithmic function, and the human brain actually hears frequencies. It doesn't hear noises, but the brain converts all the frequencies. And we have to do that within the computer if we want to recognize voices right there. So that's there. One of the very interesting things is that as we age, this part of the ear actually tends to deteriorate first. So when you get to be an old man like myself, you don't hear the high ends as well as you do the low ends. That's why older men are often accused of ignoring their wives. Women have deeper, higher pitched voices than men. Most men have a deeper voice. After puberty, the men grow, the larynx, the voice box sticks out. And one of the things that happens with a 13, 14-year-old boy is their voice gets lower in pitch. Girls don't do that. They tend to have a higher pitched voice. So as men get older, and maybe this is Allah's way of telling men it's okay to ignore their wives, but as men get older, they don't hear the higher pitches as well as they did when they were younger. So when a man gets around 70, 75 years old, sometimes he has a hard time understanding his wife. And it's not because he's a crankety old man and is ignoring his wife. He can't hear a lot of what she says because the higher frequencies in the ear are not working. These hairs down in this end right here tend to get stiffer as they get older, and they don't vibrate as easily. So, but that's my biology lesson on hearing right there. And I did my master's thesis was on voice. Actually, it was on voice rehabilitation by looking at the harmonics, coming from consonants. So whenever I can, I try to impress people, but I do know something about how the ear works right there. So that's it. Okay, getting back to, and somehow we got totally messed up when I did that. Right there. So, okay. So what we've got here is we've got the whole concept right here is that we've got this transducer. And what we've got is sensors taking physical parameter and converts it to an electrical, an actuator converts electrical input to a physical output. So we've already talked about actuators. Actuators, for the most part, are motors of some type, right there. They could be actually LEDs or lights or speakers or something like that. Typically, when we look at an actuator from the robotics world, it's almost always going to be a motor right there. But in the real world, it could be a human, it could be a voice. So piezoelectric takes a force, converts it to voltage right there, or we can take a voltage, convert it to a force. Sound, microphones, loudspeakers right there. So again, for many, many of these things, there's a counterpart when we look. However, thus far they've failed, fortunately, to create, and they've actually been working on this. So I'm not crazy here in saying that this has been a research project probably for 30 years. They've yet to perfect it to create an electronic smell generator. They have been working on this for many, many decades, to where when you're sitting there watching a movie on television or in a theater, the smells from the movie will then radiate into the audience right there. So I'm thinking that it's probably a good thing, looking at some movies, that they don't have that feature. Imagine watching CSI, and they walk into a room with a corpse has been there for 3 days. I don't think I want that smell in my living room right there. So, but regardless, but we're looking at force motors right there, or up to there. Sound speakers. So some of these have counterparts, some do not, right there. So there's a list of all the commonly detectable biological, right there. We're looking for the presence of a particular chemical in the blood. One of the things my wife does every morning, she's a diabetic, is she pokes a hole in her finger, and she takes a drop of blood and sticks it into this little machine. It comes back and says some magical number that says, you ate too much chocolate yesterday, or you better hurry up and get something to eat or you're going to pass out. But I mean, there's a range that that she needs to have her glucose level within, right there. So that's actually falls under the biological and chemical both. That's there. I used to be short and I'm short of it again, a particular hormone in my blood, so I was taking supplements, injections to replace it. That there, unfortunately, the hormone shots I was taking caused my blood to get thick and caused that there. But one of the things that how I found I was short that there is that I did a chemical test. That there, and this is done in a lab with electrical sensors for the most part. Electric, of course, you've looked at electric sensors. I mean, those are voltmeters, ammeters, those types of things. You've seen those. Electromagnetics, there's sensors to measure the electromagnetic field of a particular object or that there. Actually, most radio receivers are electromagnetic sensors right there. Radio waves are a form of electromagnetic signals right there. Common ones that we see in robotics are heat and temperature, right there. We want to measure the temperature of something, right there. That's important if you're cooking. I like to eat steak. I'm from a steak part of the country. I'm upper Midwest, Minnesota, Iowa. So those are big beef countries. States we produce a lot of cattle and dairy. So I like to eat, a nice T-bone or ribeye steak, that there. And when I'm cooking it, I want the inside of the steak to be a certain temperature because that relates to a certain doneness. And unlike most of you that there, I like mine rare. A good steak, you want to see some blood in the steak. I know that if I cook that for any of my friends, that they come and they look at that steak, they see the blood, they run. That's not done, that's not cooked. But magnetic, we want to be able to sense magnetic. Magnetic is used in a lot of places in robotics as far as we place magnets in certain places and we measure Hall effect sensors. We'll rely on that. Displacement, this is a whole family right there. I don't know what mode I'm in now. Oh, I don't know what that was again. I guess this is where I'm supposed to be right here. Okay. Right there. I'm on the wrong page. I went to the download page. That's why my pencil wasn't working right. So, but displacement, velocity, acceleration, those questions will actually pop up on the final exam as well as midterm. I will ask you for examples of each of those right there. Optical sensors right there. I've worked on several projects where we had optical sensors. One project I worked on went on a tractor out in the farmer's field, and this tractor had a big arm that stuck out from the side of it, and it would pick tomatoes off of the tomato vines. That's there. Well, it also picked up clumps of dirt, and it picked up green tomatoes, red tomatoes, black tomatoes. It picked up good tomatoes and bad tomatoes. So we had various sensors that were along this arm that would look at the color of the tomatoes, and if it wasn't red or green, chuck it out. We didn't want it. If it's green, it can be harvested, but then placed in a ripening chamber to ripen or be used for certain types of stews and things like that. If it's red, it's good. If it's starting to show brown, it's sat on the field too long, it's no good. If it's brown, it's likely to be a chunk of dirt or a rock. So, but again, we had optical sensors that looked at that. I worked on a project, and probably the longest I ever worked on a project, and it failed. And Well, the reason it failed, I wasn't the chief engineer. The chief engineer and the owner of the company made a design error early on. And engineers don't do design errors. They oversights. They underestimate or overestimate the accuracy of the sensor. But what we were doing is we were looking at potato chips as they're coming. Actually, we were looking at potatoes at that point, but we were looking at the chips later. But we were looking at potatoes as it came down a tube, and we were looking for black and red or black and green spots on the potato. If the potato had too big of a black spot or too big of a green spot, we would reject it to make potato chips. And then after the chip was cooked, we would look at it again and throw away any chips that were not good. So this is for an automated potato chip factory, obviously. The sensor that checked the potatoes chips themselves worked, but the one that didn't look for the potatoes didn't work. We should have used the camera. But Sam said the cameras were too expensive. So we spent a year and probably $1 million of time discovering that is not putting the camera in. Not only did it not work, but it also cost us a contract. They went to a different company to buy their sorter. But regardless, sometimes you make those mistakes, and this particular one, I'll point the finger at the guy who made the mistake. Simply because he owned the company and he overrode us pure junior engineers out of this question. This is money. I didn't care. That's it. So optical radioactive sensors right there. So there's various ways that we can do this. I'm not going to go into this. This particular slide was not in my others. The physical we're actually bending something typically somehow. The one that I'll talk about one in particular, but as we look at all these, there's various ones here. But let me just kind of point out one that jumps out that I can come up with an easy example off the top of my head. Is a thermal elastic right there. In thermal elastics sensors, basically, if we look at an old style thermometer, a household thermometer, or a thermostat in a car, what it's got is it's got a metal spring that's anchored in the middle right here. And then it's got a glass tube right here that's got a level of mercury that floats there. Usually it's mercury, it's electrokinetic. It's a metal that will stay a liquid in at room temperature for a wide range. So mercury is quite often used. Mercury is deadly poison, but it's been used a lot for thermal measurements right there. And then it has two little conductors here. So now the way that I showed this, I showed that this liquid floating there. If it's in this position, most likely the liquid's going to be like this, right there. In which case, the thermostat would close those connectors. Now, if it's like this, right here, and here's our two little conductors, most likely our liquid's going to be here. So as we heat this spring up, it actually moves a little bit right there. So when it's cold, it contracts and it might look like this right here. So when it's cold, it's like in this position, the air con is turned off. We'll say this is an air conditioning method. When it gets too hot, the metal expands. When it expands, it moves the sensor over to here. It puts a short between these two connectors, and the air conditioner turns on right there. So this is one type of mechanical sensor that measures temperature by looking at the expansion and contraction right there. And this converts it to, now this is a binary sensor right there. And when I say it's binary, it means that it's either on or off. And the way that we used to adjust these is when you look at the front of these, there was a little knob and you would set your temperature that where you wanted the heater, the air conditioner to turn on. That would actually turn this little spring inside there. That's there, and then of course the temperature would change it. Those aren't very common anymore. Now, most of the time if we want to measure temperature, we use a thermocouple, which is two metals that have different coefficients of conductivity, or we use a semiconductor type, what was it, I want to say the TL34 and 35 is a common one. That particular one is it's got 3 wires coming out of it. VCC comes through here, ground comes from here, and here is a voltage, but this voltage is based on the temperature. And we can then, it's usually 1 millivolt per degree Celsius. It's nice linear scale. This is a design IC. This is not a transistor. It looks like a transistor. But most of the time when we measure temperature, we use a thermal semiconductor sensing mechanism. This design was actually designed back in the 1920s. We're talking 100 years ago, and it existed for a good 80 years before they started disappearing. I've actually owned multiple homes, and I grew up with this type of temperature sensor right there. So I'm very familiar with it. Most of you probably have never seen one right there. And the reason you probably have never seen one is that heat is not a major thing that you find in a Malaysian home. Air conditioning is, but air conditioning really didn't become popular in Malaysia until the last 10 to 20 years after the electronics temperature sensors became very prevalent. So the mechanical temperature sensors really never took off here. You will find them in the engine of your car, because the reason you'll find them in the engine of the car is that it's not for measuring the temperature as much as it is for opening, closing the radiator to allow coolant into the engine, to cool the engine down. There. Now, again, in Malaysia, you may not, because you may not need a thermostat. I grew up in Minnesota where it gets to -40 in the wintertime. You don't want that water running through the radiator, cooling the engine down until it gets warm. You want that engine to get warm because you want heat in the car, because that car is cold. So we have a thermostat that would not open up until the temperature got up to like 180 degrees Fahrenheit, and then it would allow the water. It would keep the engine cool enough to where it didn't damage it, but it would allow it to get warm enough to where it would get the oil thick enough or thin enough to run into the engine. Because that's the other problem with cars, is if the oil is too cold, but the oil pump can't push it up to the cylinders. If it doesn't push it up to the cylinders, it causes the cylinders, the rings to rub against the walls of the cylinder, which causes friction, gets very, very hot inside the cylinders, and eventually causes the engine to blow up. And I've had one engine blow up because of a clogged oil vein right there. Just like I have several brain cells that blew up because of a clogged blood vessel, I had an engine blow up because of a clogged oil vein right there. Same cause right there. Okay. Yeah, I'm getting a little sidetracked on these here, but that's it. Okay. And let me close this one here. Let me go to this one here. All right. So we've got chemicals are that's a relatively complex design, but basically the chemicals sensors that I've worked with are more like the thermal electronic sensors. It looks for some type of reaction from the chemical with a particular material that you place into it in order to sense how much saltiness there is to it, how much sweetness there is in the blood. It looks for that there. Biological is the same thing. I don't treat biological and chemical differently. They're really the same type of sensors right there. Now, there are biological sensors that measure electrical waveforms for like an EEG. You attach it to your brain, to your skin, and it measures the electrical energy going on inside the brain right there. There are sensors that look for sound. Has anybody ever taken a blood pressure? Right there. When you look at blood pressure, here's your arm, there's a cuff that goes around it. This goes to the blood pressure meter right there. And this is just a hollow tube, really, is all it is. And what it's looking for is that this thing, it's got a wire that goes to it that tightens up the blood pressure cuff, tightens it up where it cuts off the circulation. That's there. It slowly opens it up and it looks for two sounds. The first sound is the veins opening up and you'll hear a shh, a really nice clear shh sound. Actually, that's the second sound. The first sound is they'll hear the blood pumping. Pump, pump, pump. You'll hear the blood going through the arteries first. And that's the upper level. And then with a little bit less pressure, the veins will open up and that's where you'll hear the shh right there. You know, at one time I learned how to do blood pressure by hand. And if you go to some doctor's office, you'll see them put the cuff on you and they got the little thing with a ball that they squeeze and the mercury goes up. And then they slowly let the air out of the cuff and you see the mercury go down. And he's got the stethoscope on your arm and he's listening for those same sounds that the computer chip in the automatic blood pressure cuff is looking for. So again, but that's looking for sounds is what it's looking for. It's not really measuring the blood pressure itself. There's no way of measuring the blood pressure itself. What it's looking for is that what pressure around your arm does the blood start flowing through in both the positive direction, that's the heart beating, that's the upper level. And that's why if you go to the doctor's office, you'll quite often see the thing do this up and down, right there, up, down, up, down, up, down, for a small range. That's because when the blood is going through, it takes the pressure up a little bit. When it stops going through, it drops it down. And then eventually the arteries or the veins open up and the blood will flow through. So again, but this is something that will measure blood pressure. So it's a very common type of sensor up there. I have a blood pressure cuff. After I had my stroke, the first thing that they want to check for is your blood pressure. And I actually suffer from low blood pressure. If you would believe that, being 30 kilos overweight, that I have low blood pressure, but my family has low blood pressure. That's there. So when they put me on blood pressure medication like they do for every stroke patient, my blood pressure got too low. And I was seeing blood pressure of 89 over 56 and things like that. I mean, I was passing out because my blood pressure was too low. There. Now, without blood pressure medications, like 125 over 60. So, but again, these are biological, but most biological sensors are actually using some type of physical characteristic right there. It's measuring something. I gave the example of the EEG signals. Those are measuring electromagnetic waves right there. When you're looking at blood pressure, we're looking for sounds. That's there. You know, there's other things. I have sleep apnea. Now that one you can believe with my weight. I have sleep apnea. I stop breathing when I'm sleeping. So I have a machine that I put on that blows air into my throat to keep my throat open, and it senses if I stop breathing and increases the pressure right there. So here we've got some various, where am I on time? Oh, we got a good 20 minutes before I have to start thinking about winding down. I can keep talking for a while. That's there. So acoustic, we're measuring amplitude, phase, polarization, spectrum, wave velocity. There's all kinds of things we can measure acoustically. When I was doing speech recognition, you know, when I was working on my master's, we were actually looking at the spectrum. Where was the frequencies in which the sound was? What was the harmonics right there? The human voice has typically two parts to it. One is the bass frequency, and the other is right there. You know, when we look at a particular sound, it has a bass frequency and a harmonic right there. And typically how we come into this harmonic right there, this is a vowel sound, and a constant is a change. You know, we're changing, but cat, the A sound, cat, and then T is the constant. And that forms the word cat. So it might look like this when we look at it, you know, acoustically right there. But we're looking here is we're looking at time, and we're looking at frequency in this direction right there. So when we're looking at acoustic sounds, if we're doing speech recognition, quite often we're looking for spectral information. We're not looking for how loud the person says cat. We're looking to recognize the word cat. And cat starts with a sound, and ends with a sound, and has a ah sound in between. So we look for each letter or phoning as a different. And I'm terrible with languages, but I understand how words are formed fairly easily. Biological and chemical, we're looking for fluid, for concentrations. There's lots of sensors out there that will measure, for example, various gases. You know, methane gas is one that you want to find quickly if you're in a coal mine. That there before it blows up and kills a bunch of miners. At one time, before they had methane gas sensors, what they used for methane gas sensors was the old canary. And this sounds like a very cruel thing, but if you worked in a coal mine back in the 1890s to the 1930s in West Virginia or near Liverpool, England, or anywhere where there's coal mines, because England has lots of coal mines, the U.S. has lots of coal mines. And coal was used a lot to heat homes, drive trains, things like that. But when you're digging coal mines out with people down in the coal mine, they always took a bird down there in a cage. You know, and what they discovered is that if there was a gas emission coming from the rocks, you know, methane gas, that the bird passed out before the humans did. So they would sit there and they would watch the bird, and if the canary died, get out of the mine was the general rule. Normally the canary didn't die, it just passed out, but sometimes it died. But they always carried the canary, and the canary was their gas sensor. Now, fortunately, we've got electronic gas sensors that they carry down the mine. Each coal miner carries it on their shirt, and they don't have to kill any more canaries back there. But the canary was an early form of measuring gas levels in the mine. That's there. Carbon monoxide is another one that you want to measure in homes. It's not as common in Malaysia as is the U.S., but every house in the U.S., pretty much on every floor, I had 3 of them in my house back in Indiana. We had fire sensors that had carbon monoxide sensors built into it. Because when a fire burns, it emits carbon monoxide, and most likely the carbon monoxide would trigger the smoke detector. Actually, it also measured smoke. It had an optical sensor that would look for if there was smoke you couldn't see between the two sensors. It was great when your wife didn't know how to cook too. I mean, you always give her a hard time, about she set off the smoke detector when the dinner burns, right? That there. But the whole idea, the reason they were so common in the U.S. versus Malaysia is that in the U.S. we tend to build houses out of wood and drywall, which burns real easily, right there. Most Malaysian homes are built out of stucco over brick, and I could sit here with a lighter for 15, 20 minutes and I couldn't light this wall. I couldn't. I could strike a match within 5 feet of this wall in a U.S. home, and it might catch fire right there. It wasn't quite that bad, but they were saying, I was reading some statistics. Your home was more likely in the U.S. to be destroyed by fire than it was to be burglarized. In Malaysia, someone breaking into your home and stealing your stuff is probably much greater than the chances of it catching on fire. That's why you got bars and grates in front of us there. Most U.S. homes, you could not have a grill like you do here. The problem with the grill like you got here is that you use a padlock on it, right? So you go to bed at night, what do you do with your grill? You lock it, right? 3 in the morning, there's a fire. You're panicking. The house is filled with smoke. Where's the key? The fire department comes to rescue you. Where's the key? So locking grills don't exist in places that have wooden structures because you need to look at fire protection. Now, recently at Dr. Carmont, there was a fire. Now, it was not an accidental fire. Someone deliberately set the fire there at one of the schools. But one of the reasons the casualty count was so high was the grills were locked. The kids couldn't get out. So, that is an issue that you have to deal with right there. So, okay, electric, I'm not going to talk about. Magnetic, we're looking at various parts of that. I'm not going to get into that. That's there. Optical, of course, we're looking at reflective index, reflexivity, absorption. Optical, we also have color sensitivity, right there. Color is a major thing that we're quite often looking for. And the way that we normally measure, we're just measuring color, is we have different colors, LEDs that we light, and we measure the amount of light that's reflected back. So it's the absorption is how you measure color, right there. Cameras are a totally different issue right there. Cameras have typically 3 sensors per pixel, and they're going to measure the red, green, and blue content of the light, and the number of pixels you have and the density is going to tell you how accurate the image sensor is. That they're thermal and mechanical. And I was checking the time, and I don't care about the time. As I said earlier, that come Thursday, I got a point in which that's there. So let me see. I'm definitely way short of my normal 1 hour, but that's all right. Yesterday I talked for 1 hour and 30 minutes. With that, my throat's giving out, so that's there. So I'm going to go ahead and stop.